Linear Algebra and Calculus, Module 1, Part 1. In this part, we are going to see matrices and some of the concepts relating to that. Arthur Cayley discovered matrices in the year 1860. Matrices have been found to be of great utility in many branches of applied mathematics such as algebraic and differential equations, mechanics, theory of electrical circuits, nuclear physics, aerodynamics, and astronomy. With the advent of computers, the usage of matrix methods has been greatly facilitated. A matrix is a rectangular array of elements or numbers arranged into rows and columns. If the matrix has m rows and n columns, then it is called as an m by n matrix. In general, it is written as A is equal to matrix in which the elements are generally denoted as A11, A12, etc. A1n in the first row, A21, A22, etc. A2n in the second row, and in the last row, specifically in the mth row, AM1, AM2, etc. AMN, which is equal to in which each of the elements are generally denoted as matrix Aij, where I indicates the row number and J indicates the column number. Next is types of matrices. The first one is square matrix. A matrix is called a square matrix if the number of rows and the number of columns in the matrix are equal, that is m equal to n. An example is given as matrix A equal to 1, 2, 3, 4, 5, 6, minus 1, 0, 2, which is a square matrix of order 3, or it is a 3 by 3 matrix. Next is a row matrix. A matrix is called row matrix if it contains only one row and its order is 1 by n. Here is an example of a row matrix, matrix 1, 3, 5, which contains only a single row and 3 columns. Next is a column matrix. A matrix is called a column matrix if it contains only one column and its order is m by 1, where m indicates the number of rows. Here is an example of a column matrix, matrix 3, 7, 1, which consists of only one column and 3 rows. Next is zero or null matrix. A matrix is called a zero matrix or a null matrix if all its elements are zeros. Next is diagonal matrix. A square matrix is called a diagonal matrix if all its elements other than the diagonal elements are zeros. An example is given over here, named as A equal to matrix, which is a 3 by 3 matrix, and as you can see, all the elements in the matrix other than the elements in the principal diagonal or in the leading diagonal are zeros. Next is a triangular matrix, a square matrix in which the elements below the leading diagonal elements are zeros is called an upper triangular matrix. Here is an example in which you can see the elements in the principal diagonal or in the leading diagonal are 1, 4 and 5, and all the digits below to that principal diagonal elements are zeros. Hence it is an example of an upper triangular matrix. A square matrix all of whose elements above the leading diagonal elements are zeros is called a lower triangular matrix. An example is given over here. As you can see, the elements in the leading diagonal are 1, 3 and 4, and all the digits above to that are zeros. Hence it is an example of a lower triangular matrix. Next is a scalar matrix. A square matrix is called a scalar matrix if all its non-diagonal elements are 0 and all diagonal elements are equal. Here is an example of a scalar matrix in which all the diagonal elements are 4 and all the non-diagonal elements are zeros. Next is unit matrix or identity matrix. A unit matrix can be considered as a special case of a scalar matrix. A scalar matrix in which each diagonal element is equal to 1 is called the unit matrix or identity matrix. An identity matrix of order n is denoted by In. Here is an example of an identity matrix of order 3, which is denoted by I3. Next is symmetric matrix. A square matrix is called a symmetric matrix if Aij equal to Aji. An example of it is given over here. Matrix 1, minus 1, 3, minus 1, 2, 4, and 3, 4, and 3. In other words, a square matrix A is said to be a symmetric matrix if A transpose equal to A. We will see the concept of the transpose of matrix after one more type of matrix. The next one is a skew symmetric matrix. A square matrix is called a skew symmetric matrix if Aij equal to minus Aji. An example of a skew symmetric matrix is given over here. It is matrix 0, minus 2, minus 3, minus 2, 0, 1, and 3, minus 1, 0. In other words, we will call a matrix A as a skew symmetric matrix if A transpose equal to minus A. Now we can see what do you mean by A transpose or the transpose of a matrix. The transpose of a matrix A is a matrix obtained by interchanging the rows and columns of the matrix A. The transpose of a matrix is denoted by A transpose or A dash. An example is given over here. If A is a 2 by 3 matrix, the A transpose is obtained by just interchanging the rows and columns, and accordingly the order of the transpose will be a 2 by 3 matrix. Now about addition and subtraction of matrices. Two or matrices can be added or subtracted if they are of the same order. An example is given over here. If matrix A is equal to 1, 2, 0, minus 7, 2, 6, B equal to matrix 6, 9, 5, minus 3, 2, 7, and C equal to matrix 4, 3, 2, 0, 0, 1. You are asked to find A plus B plus C and B transpose. Here, addition of these three matrices is possible because all the three matrices are having the same order, namely 2 by 3. Okay, so if you are adding the matrices, it is denoted as A plus B plus C. For adding any number of matrices, just add the corresponding elements in each of the matrix. So in the matrix A, the element in the first row first column is 1, and that is added to the first row first column element in matrix B, which is 6, which is again added to the first row first column element in matrix C, which is 4. So on adding 1 plus 6 plus 4, you are getting as 11, and that is actually positioned in the first row first column of the resultant matrix. Similarly, we will add the digits in the corresponding rows or in the corresponding positions of each of the matrices to get the element in the corresponding position in the resulting matrix. So, as a result, on doing the corresponding adding, we are getting the resultant matrix as matrix 11, 14, 7, minus 10, 4, 14. Now for getting B transpose, we are provided with B, which is matrix 6, 9, 5, minus 3, 2, 7. We are just interchanging the rows and columns. Here 6, 9, 5 is actually the row on matrix B, and on interchanging it, it will become the column in B transpose. Similarly, the second row, which is in B, which is minus 3, 2, 7, had become the second column in B. So we got B transpose as 6 minus 3, 9, 2, 5, 7. Next is multiplication of matrices. Two matrices can be multiplied if the number of columns of the first matrix is equal to the number of rows of the second. Example, find matrix AB where A equal to matrix 1, 5, 7, 0, 6, 8 and B is equal to matrix 7, 8, 9, 8, 6, 5. Here, these two matrices can be multiplied because the order of matrix A is 2 by 3 and the order of matrix B is 3 by 2. That is, the number of columns in matrix A, which is equal to 3, is equal to the number of rows in matrix B. Hence, multiplication of these two matrices is possible. So, for multiplying two matrices, we will, for getting the first row, first column digit in the resultant matrix, we have to multiply the first row elements of matrix A with the first column elements of matrix B and we have to add them. Then we will get the digit in the first row, first column position of the resultant matrix. Similarly, we will operate the other rows and columns to get the digits in the corresponding positions of the matrix of the resultant matrix. Now, moving to the concept of determinant of a matrix. Determinant of a matrix is denoted by det A, or symbolically it is denoted as det of A. Consider the example matrix A equal to A11, A12, A21, A22. Then for getting the determinant, we will just multiply the digits in the leading diagonal of the square matrix and that is subtracted, that minus the multiplication of the digits, namely A21 and A12. So, det A is equal to A11 into A22 minus A12 into A21. So, that's about how to find the determinant of a 2 by 2 matrix. Now, if we are considering a 3 by 3 matrix, matrix A which is given over here, the determinant is obtained by det A is equal to A11, which is actually in the first position of the matrix, that into determinant of A22, A33, A32, A33, which is a submatrix obtained by deleting the row and column containing the element A11. Okay, minus we will write the digit in the first row, second column, that is A12, into determinant of the submatrix that is obtained by deleting the row and column containing A12 plus the next digit in the first row, that is A13, into determinant of the submatrix that is obtained by deleting the row and column containing A13. So this is the rule of how to find the determinant of a 3 by 3 matrix. Next is submatrix. A submatrix obtained from a given matrix A by deleting some of its rows or columns or both is called a submatrix of A. That is, a matrix obtained from the given matrix by deleting the corresponding rows or columns or both is called as the submatrix of the given matrix A. Now we are going to discuss some of the elementary transformations or operations that is possible with the corresponding rows or columns of the given matrix. Let A be a given matrix, then any one of the following operations on A is called elementary transformation or operation on the matrix A. The first transformation is interchange of two rows or two columns. The interchange of ith and jth rows or columns is denoted by Ri, which is put as a double-headed arrowed line, Ri to Rj, as well as Ci to Cj, Cj to Ci also. Next transformation is multiplication of the, this is an operation using the rows or columns, that is multiplication of the elements of row or column by a non-zero number k. The multiplication of ith row by k is denoted by kri and ith column by k is denoted by kci. Addition of k times the elements of a row or column to the corresponding elements of another row or column, k not equal to 0. The addition of k times the jth row to the ith row is denoted by Ri tends to Ri plus krj. The addition of k times the jth column to the ith column is denoted by Ci tends to Ci plus kcj. Next is equivalent matrices. Two matrices A and B are said to be equivalent if one matrix can be obtained from the other matrix by performing a finite number of elementary operations. Two equivalent matrices are written as A equivalent to B. It is actually read as A equivalent to B, and the symbolic notation is using the symbol tilde. Consider a matrix A equal to, which is a 3 by 3 matrix which is given over here, matrix 1, 2, 3, 1, 4, 2, 2, 6, 5. And another 3 by 3 matrix which is B equal to matrix 1, 2, 3, 0, 2, minus 1 and 0, 0, 0. We have to show that A is equivalent to B. Here, A is equal to matrix 1, 2, 3, 1, 4, 2, 2, 6, 5. We will get it equivalent to 1, 2, 3, 0, 2, minus 1, 0, 2, minus 1. That is actually obtained by doing some row operations with the given rows. That is, if you are subtracting the second row in the matrix is obtained by subtracting the first row from the second row, so that you will get the elements as 1 minus 1, it will give 0 in the first row, second row, first column position. And if you are subtracting the corresponding second digits in the first and second row, that is 4 minus 2, it will give 2, as well as 2 minus 3 gives minus 1. So similarly, we are operating the third row with the first row by the operation R3 minus 2R1. On doing like that, you are getting the third row in the matrix. Now, we will get an equivalent matrix from this matrix by doing the operation R3 minus R2 in the resultant matrix. So, we will get the matrix as 1, 2, 3, 0, 2, minus 1 and 0, 0, 1. And as you can see, it is actually a upper triangular matrix. It is an upper triangular matrix, and so we can say that therefore these A and B are equivalent, because that upper triangular matrix is actually the B that is given over here, and we have obtained B from the given matrix A by some row transformations or row operations. Therefore, we can say that the given two matrices A and B are equivalent. Next is rank of a matrix. The rank of the matrix is the order of the largest square submatrix whose determinant is not 0. Or in other words, we can define the rank as a matrix A is said to have a rank R if there exists at least one square submatrix of A of order R whose determinant is not equal to 0 or which does not vanish. All square submatrices of order R plus 1 must vanish if the matrix A contains any square submatrix of order R plus 1. Then the determinant of every square matrix of A of order R plus 1 should be 0. So if a matrix is satisfying these two conditions, then the corresponding R will be the rank of the matrix. And the rank of a matrix A is denoted by row of A. Now we can see an example where we are asked to find the rank of the given matrix. So find the rank of the matrix, which is matrix 1, 2, 3, 1, 2, 4, 6, 2, 1, 2, 3, 2, which is actually a 2 by 4 matrix. We have to find the rank of this matrix. For that, first we will find the minor of a submatrix of the given matrix, that is M1, which is equal to dit of 2, 3, 1, 4, 6, 2 and 2, 3, 2. If you are taking the dit of that matrix by applying the formula for finding the determinant, you are getting it as 0. Similarly, on taking the minors of the other submatrices of order 3, we are getting all those minors as 0 as it is given over here. All the minors of order 3 are vanishing here, and there exists a minor, namely determinant of 6, 2, 3, 2, which is equal to 12 minus 6 equal to 6, which is not equal to 0. That means it is not at all vanishing. Therefore, according to the definition that we have, that is discussed over here, the rank of the matrix is 2. Since we got the minor of a 2 by 2 submatrix of the given matrix as not equal to 0, we concluded that the rank of the given matrix is 2. So that's all from this topic. Thank you.